Okay, so today we're talking about evaluating visualizations, and here's... I have started, yeah. We're talking about evaluating visualizations. So this is really, really, really important because you need to know what you are doing, essentially, and whether it works. So when you're creating your visualization, you want to work out whether it works. You don't want to work out whether it works. It won't work. Okay, well, you find out. Okay, so you are working with Edward Tuft's principles for excellent graphics, and you'll be aware that there are lots of different sets of principles depending on what mood Edward Tuft is in, but with every book comes a different set of principles. Here are some of them. So you know all this because of the essay, right? So you've got his principles suggest that well-designed, complex ideas, lots of ideas in the shortest time and the smallest amount of symbols in the smallest space. They're multivariate, and they require that you tell the truth. Okay, so that's what Tuft reckons. So that's all well and good, but how do you know whether what you're doing is that? So you can think about it as you're creating it, but it's also worth thinking about how user-friendly is it, and have I actually performed, have I done what Tuft wants me to do, if you agree with these principles. Maybe you don't. And you're used to Crack's web map types. You're working with that as well, right? So you've got all these different things, so you want to think about whether what you're doing fulfills the classifications that you want your visualization tool to fulfill. So, for instance, you started off thinking, I want to make an analytic, interactive web map, and how do you work out whether you're actually doing that? Is that better? The lights? Okay. I think it can go even darker if you like. This way. Okay. Okay, fine. So you've got Crack, you've got Tuft, and you're doing your essay based on this stuff, right? So essentially, what we're asking you to do is to evaluate a visualization using these classifications. So the principle of doing an evaluation is to set in advance what your principles are, and then decide whether the thing that you're evaluating conforms with those principles. What you don't do is think, okay, I want to do a really good piece of work, let me think of all of the different ways that it could be better or worse. I mean, that's one approach, but it's not kind of systematic. So the systematic way of doing it is to decide in advance what your criteria are. Does that make sense? Cool. Okay, so when we're talking about evaluating visualizations, you want to think about how well does a visualization work? That's the basics of it. Why is it important, and how do you go about testing it? So that's what we're going to talk about. So why evaluate a visualization? What's the point? So here is a list of some things that might be suggestive of use. So you might think that it's useful to discover some fundamental truths. So this is, you can use it, you can use an evaluation to gather your empirical data. And that might not be to do with how well does the visualization work, but it might be more about how do people use the visualization in a way that tells us about human perception. Does that make sense? So you're not so much evaluating, I mean, you're evaluating the visualization, but you're not so much doing it for the sake of the visualization structure, but more for the sake of human cognitive processes. Yeah? So how do people perceive phenomena? Right? How many flashes of light? How fast do you flash a light before it turns into one continuous light, for instance? That's a really simple experiment that you could do, where you can do things using visualizations to do that, computer-based visualizations. It could be to do with cognitive modeling, which is about how people, how your brains work, essentially, what task processes are, and which bits of the brain do what, so you can work out how well people, how do people respond to a visualization, and you can work out ways of getting inside people's heads using MRI or other things like that. So how do people perceive patterns in motion? Well, you show them a visualization of patterns in motion, and then you see what their brains are doing, or see what the results are in how they respond, one way or another. So that might enable you to discover some fundamental truths about how, assuming you believe in fundamental truth, which you don't necessarily, but it essentially allows you to do some sort of scientific experiments about how the brain works. The next thing is to see if theory generalizes to practice. So you might have decided that you've got a result that works in the laboratory, you've tested it under controlled conditions, how well does it work in the wild? So that might be one reason for evaluating your visualization. Or you might have set up different ways of doing something and you want to work out which one works best. You want to impart some information or you want to discover something. Either way, you do more than one visualization and get people to do all of them, and then you work out which one has the best results. So you can compare your methods, or you can compare your interfaces, or your systems, or your structures, or whatever else it might be. All those make sense so far? Cool. Okay, so you might want to measure the task performance, so how well people actually perform a task. So how often do they do it wrong? How badly do they do it wrong? Error rates and magnitudes. Not how often do they, and that might be to do with people, or it might be to do with the process that you're asking them to do. So it might be useful to work out whether people are bad at doing the thing that you've asked them to do, or whether the thing that you've asked them to do isn't set up for the way that people would most usefully like it to be. Does that make sense? No. So it might be that you want to work out whether you've set up a good system, or it might be that you want to work out whether people have the innate ability to do the thing, to perform a task. So you could be testing either of those. Yeah. You might want to find out what people prefer, how people like using the thing that you've set up. So does it look nice, or is it usable? That's a classic form and function dichotomy, not necessarily one or the other. There might be a middle ground. So you set up something and you work out, you have different ways of doing it and see whether it works that way. Yeah? Am I explaining it? Right, so and of course the final one is you've set up a visualization and you want to know if it's any good. So that tells you that there are lots of different reasons for performing an evaluation, or several evaluations, and not all of them are to do with making your visualization better. Okay, lots of different reasons why you might. So how do you go about doing it? So here are some different ways of thinking about that. So I've listed a few, but there are lots of broad ways of thinking about the things that we're going to talk about. So I thought we'd talk about psychophysics. Have you heard of psychophysics? Okay. So psychophysics is described or defined as the scientific study of the relation between stimulus and sensation. So what's actually going on when our bodies are stimulated in some way, our senses are stimulated, what's going on between the event and our perception of it? Yeah. So we aren't very good at knowing how our brains work and how our nerves work and how we make up our minds about things and so on. So psychophysics is an attempt to use principles of physics to work this out. So what are the sensory dimensions of our senses? Yeah. So for that you've got to measure things very finely. So if you're taking a psychophysical approach to your geovisualization, for instance, you would want to make sure that everything is controlled very carefully, because the idea is that quite small changes can have quite big effects. So it might be that you want people to evaluate your visualization and you set them up in a room, and the room has got different light levels at different times of the day. And that's not a controlled environment. So you need to control for that sort of thing if you're working in a psychophysical environment. Yeah? So light levels, temporal characteristics, what time of day it is, obviously, or how long it takes to do it, and spatial characteristics. So you have to think really carefully about how you set that up. So, for instance, you've got something like threshold measurement, which is to do with how fast must light flicker before it is perceived as steady, with that idea. So when do we start to notice things? So we notice things that are moving rather than things that are static, for instance. So how fast does something have to move before we notice it in the background? Or for another example, changes in volumes of sound. Yeah, so, and the other examples that you can see. So these things can be useful because you might have lots of different, for instance, different classifications of your data. And you want to work out whether whether your users can even tell the difference between those classifications, the way that those classifications are symbolized. Do you need fewer classifications, fewer classes, fewer breaks? Or do you need a better way of differentiating between the breaks? Yeah? So it might be something like that. Or more physical things like how many hairs on the back of the hand, etc. So which of these lines is longer? The right one, the same? Almost as if they're the same. Almost? Mm-hmm. Go on. You reckon they're both the same? You reckon they're both the same? You reckon it's the same? It's not a trick. The one on the right is longer. Yeah. It looks thicker. Thicker, closer. It's got exactly the same shading. It's exactly the same thickness. It's just that this one is longer by maybe 3 or 4 pixels, I think. Really not long. So that's not enough to tell the difference, right? So if your classes of data are represented by something by different things that are of that order of magnitude of difference, then, I've just performed a little evaluation exercise and it turns out that nobody can tell the difference. You reckon they're the same. So you probably want to have different classes or different symbols. Right? So it can be that easy. This isn't a controlled environment, obviously, and maybe I could ask 100 people, but I specifically set this one up so that you probably wouldn't be able to tell the difference. But, Peter, your original thought was that the one on the right was longer. And then you changed your mind. Why did you change your mind? Okay. So we fool ourselves, and then we start thinking, maybe he's bluffing. Maybe it's a trick. Maybe he's trying to prove some point. I'm trying to prove a point. The point is that one of them is longer, but you couldn't tell. That's all. Okay, so you could use your evaluation to discover things about error rates to do with human perception. So, what proportion of stimuli are perceived by users on average? That might be one way of doing it. So you could get 100 people to use a visualization and discover how many of them can tell the difference between those two lines. For instance, you might want to work out whether individuals perform better or worse than other individuals, or better or worse than ideal observers, or whatever it might be. Are pilots any good at using particular sorts of visualization? So that's a really key example. Pilots are trained on flight simulators. So when flight simulators were introduced for training pilots, there was a certain amount of consternation. Does this accurately reproduce the real conditions? Flight simulator on a computer. Well, on a computer game. So what do you think? Does it accurately simulate the environment of piloting an aircraft? So what do you think? Would it? No? Why not? Okay. So there's a haptic thing that's to do with touch. So it's different in a like a box simulator that moves around. Whereas if you're sitting in a bedroom using a mouse or a joystick, then it's going to be slightly different. It's not going to be the same. But flight simulators are great for testing pilots in real life when it's properly set up. But not a game. No, not a. 2D. Yeah, although you could have a dozen screens set up if you wanted to. You'd still want your chair to rock in the appropriate manner. And not have your friends coming in offering you tea in the middle of it. Oh, I suppose that would be quite similar to how it works for pilots. But yeah, so someone has done a certain amount of refreshments. Someone has done plenty of people have done plenty of evaluations of flight simulators to work out whether it's safe to train pilots on them. Okay, so that's a real-world geovisualization or visualization example. You could use the data created by your error testing to improve the visualization. So you tweak it depending on the feedback that you get from the error data, or you give the users the system and get them to adjust it to how they're most comfortable, how they feel that they are best able to get the information or interact with the visualization. Yeah, and watch out for bias, obviously, because people will have their own comfort levels, but you might be wanting to do something that goes outside a comfort level. Or people might automatically like particular colours and want to set everything to shades of blue, for instance, whereas actually you want that doesn't help them pick out the best information or whatever it might be. Yeah. Have you come across the ideal observer analysis? The idea of the ideal observer? Okay, so the ideal observer is the theoretical device which performs the task optimally. So what do I mean by that? It's not a real ideal observer. It's not a real observer. It's not a real computer system or a real person, but it's a set of conditions and abilities. Right? So what you are aiming to get is not the performance of a task with no errors at all, but the performance of a task that's as good as it can be given the conditions that you set, given the constraints of the task system. So it might be impossible, given the way that the task is set up, to do it 100% no errors, whatever that might be. It might be impossible to pick out the moving target, or it might be impossible to discover the location, or to tell the difference between the symbols, or whatever it might be. It might be impossible, but you want to have this idea of what would be possible were it not for human error. So human error is in sort of random making a mess of it, rather than completely error-free. Do you see what I mean? Right? Okay. So you've got the two different types of constraints that go into it are the information that's available to the theoretical device and the capabilities of the theoretical device, and you set those up. Yeah? And that can be used, as I say, to compare to human performance. So how well do people perform compared to the ideal observer? And you might want to minimize that difference. So you keep tweaking the system, but keep the same capabilities, whatever it might be, until you narrow that gap. That's an ideal observer. Analysis. Then you've got this thing called signal detection theory. Have you come across this before, signal detection? There are quite complicated mathematical ways of working out signal-noise ratios and so on. Sorry? It can be used in remote sensing, yeah. So in remote sensing, you've got a system which is and from that system you're trying to get the data out of a system by working out whether you can see the signal or the noise. So you would want to optimize your system to allow that to happen. So you've got your background events going on. Which ones are the stimulus that you're looking for? So that could be to do with remote sensing, or it could be to do with, I don't know how often you do this, but let's say you tickle somebody with a feather, and at first they don't notice, right? And then after a while they scratch, right? So how much tickling needs to take place before their brains notice that it's an actual foreign object that's tickling their necks, right? Yeah. So that's the signal to noise ratio in terms of human experience, human haptic experience. Right. So detection in human is based on experience. So how have people done this sort of thing before? Their expectations. What are they expecting is going to happen when they're performing the task? What have you told them is going to happen, or if it's in a controlled environment or not? What kind of physiological state they're in, or what kind of psychological state they're in, for that matter. Does it make a difference if you're tired and you drive? So if you're tired and you drive, then you're more likely to be driving as if you were drunk. The tireder you are, the more your driving is like if you're a drunk driver, right? So you have less of an ability to spot signal, and less of an ability to respond to it, for that matter. So signal detection is based on these things. Right? All making sense? Ooh, any questions so far? All right. So another way of applying evaluation is using the tools given to us by cognitive psychology. So it's different from the sort of psychophysical. It's more trying to understand the model of how our brains work by kind of describing it as interlocking components and thinking about which bits go where, without thinking too much about the specifics of nerves and chemical processes and so on. So in cognitive psychology, the brain is understood as interlocking networks, interlocking modules of bits. So we have these metaphors about short-term and long-term memory. Does that sound right to you? The brain as a set of interlocking modules? Yeah? Yeah, maybe? Yeah, no? Uncertain? Yeah? Maybe. I mean, I think it can, it can be useful. There comes a point at which you're losing some of the nuances if you understand everything as being separate systems that are kind of interlocked or interlinked, rather than as being one system. Who knows? I don't know if if human understanding is easily understood through metaphors that encompass everything, or on the other hand, it's so complex that we have to simplify things somewhat anyway. So worth bearing in mind that there are critiques of all of these kinds of umbrella terms that we're talking about. So if you're using this approach, the cognitive psychological approach, you would do experiments to test the hypotheses about those models. Right? So you imagine that you describe a model, and then you want to test to see whether that model is an accurate reflection of the way that the brain actually works. You can do that with an evaluation. So reaction time, as I say, perceptual error rates, these sorts of things. So those are the sorts of experiments that you would see that take a cognitive psychological approach. And you would, so an example here is that you get someone to have an fMRI, and they have to do something out of the Krypton factor, like count down from 100 in 7, which I would find difficult enough without having to remember and reproduce spatial locations of objects. But the idea is that you do something quite complex and see how the brain responds to those requirements. Yeah. So So here's what your brain looks like, or here's what somebody's brain looks like, and maybe it's a combination of lots of people's brains. The bits that are stimulated in your brain when you have to sit in a room with lots of speakers around your head, and you get played different sounds coming out of different speakers, and if you hear the same sound coming out of the same speaker, then you press a button. And if you hear the same sound not coming out of the same speaker, or if you hear a sound from the same speaker but it's not the same sound, then you don't press the button. Okay? So you've got to press the button when you hear the same sound from the same place, and you get different activity in different parts of the brain depending on whether it's a transient thing, whether it's something that's requiring a response, or whether it's just background noise or not repeat. Okay? So you can see where the different bits of the brain are coloured in depending on what those are. And if you want to read the whole of the account of what's going on, then follow that link. So that's an example of that. Looks like fun. Do you want to do that for your geovisualization? No? Get people to use it while plugging them into an fMRI scanner, and yeah, there's probably one somewhere in the university you could borrow if you ask nicely. So another way of thinking about evaluating the work that you do is structural analysis. This is a bit less scientific than the other approaches so far. You use theories of cognitive processing using observations, which tend to be interviews. So you ask someone to use a visualization, and then you ask them about how they performed. How did you like doing this, that, the other? And you do it in quite a structured way, so it's not a kind of open-ended interview necessarily, but it's asking people to talk to you about their performance and what they thought was going on. So the question, one of the potential critiques of using the structural analytical approach is, are you going to end up with descriptions and classifications or an actual explanation of what's going on? So you might get a very good idea about, you might get lots of description about how people interact with something, but you won't necessarily, or maybe you will, but you won't necessarily get an explanation of why people interact in a particular way with the thing that they're supposed to interact with. Yeah? This is no value judgment. This is just to do with the limitations of different sorts of techniques. Right? So does that one make sense? And test benching, or the sandpit approach. So you basically give somebody your system and get them to use it, and then tell you what they think about it. So it's even less structured than the previous approach. It's simply fiddle with things and let me know what you reckon approach. So this is sort of in decreasing order of scienciness. So highly recommended, don't give people too many things to play with. Just give them a few things to play with and get them to talk about what they like. This is the not terrifically scientific, but it's very achievable. It's much easier to do this than the MRI scan version. Yeah. So if you need to do an evaluation, you may end up doing something like this rather than MRI scans. Yeah. Which is why we talk about this one too. So give people just a few things to change, and then you do some interviews and give them some Likert scale. Do you know what Likert scale is? Yeah? Richter scale. It's a bit like the Richter scale. Yeah, so a Likert scale, you give them, 1 to 5 on a scale of whatever it might be. Whatever do you find this thing? So how usable is this? How easy is it to differentiate the colours? 1 to 5. 5 for very, 1 for not at all uncolourable. That's a good way of developing prototypes. Okay? And you might want to apply some statistical analysis, of course, because Stats is awesome. So you can use quantitative techniques. I don't know why you're laughing. Quantitative techniques for evaluating visualization perception. So look at this genuine example of something that you might see in some first year work, certainly not in your third year work. But have you ever seen a legend or key that looks a bit like this? Right, you're familiar with that. Yeah, it's a misapplied. It should be the other one. Okay, so whatever it is, it's turned into categories, right? But the important question here, I mean, the appropriateness of the categories is one thing, but the important question is, can you tell the difference between that colour and that colour, the top one and the bottom one? Yeah? So if they were next to each other, you would probably be able to tell the difference, okay? Yeah? It's very much darker. It's significantly darker. Okay. So at some point along here, can you tell the difference between any two consecutive blocks? No. So although there's a difference between the top and the bottom, just between any given two consecutive blocks, you couldn't tell the difference. You can. Which ones can you tell the difference between, Peter? The bottom two. No? Yes? No? Yes, no, maybe. Okay, now imagine that you've got this and you've got your choropleth map next to it, right? Would you be able to tell by looking at the colours on the map which value goes with which area? Okay, so no, right? Nonetheless, maps are produced that use, maybe not as extreme examples as this, but if you've got more than 7 classes, it becomes on certain colour schemes, on the varying degrees of light and dark of the same colour, it becomes very difficult to tell the difference if you've got more than 7. Which is, yeah, why not use 5? But then that might not go with the data classification. Yeah, but so you have to work out what's appropriate. And if you have to have more than 7 classifications and you have to use different ways, think of different ways. It might be different colours exactly, or it might be different something else. But it's not necessarily that. Yeah, or you could use symbols. So it doesn't have to be colours. You can use symbols. So how many distinct textures is something you might want to think about. And how do we map those data dimensions to them? So you think about what does your data look like in real life, and how would you differentiate them, and then try and apply that to how your data classification and legend works. Okay. So statistical analysis, where does that come in? Well, don't worry, we're not going to go into detail about these things, but you are aware of these things, right? Okay, right. So principal component analysis, you don't need to tell me how this works, right? Because you know. I don't need to tell you how this works. People on the recording might not. You're quite right. Thank you. Okay, so principal component analysis, simply, as I'm going to read it off the screen, I'm afraid, turn the highly correlated variables into uncorrelated variables, principally responsible for the variation. So you see that you have lots of different variables, and you use some mathematical procedures to group them into variables that represent the variation that is there, rather than real life elements. And you can kind of work out which ones go into which, but basically what you're doing is dividing the data set into different strands of variation, right? So if you're having a problem of the sort that we looked at on the previous slide, then you could use principal components analysis to work out what to do. You could use cluster analysis. There are lots of different forms of cluster analysis. It might be to do with clusters of points in real space, or it might be in a kind of data space. It could be it could be working out when you zoom in and zoom out, when lots of points become a single point. You can use cluster analysis to do that. So when does it become a single symbol in your interaction, whatever your group of data points are? And you can use multiple regression. So if you've got a set of variables, I'll tell you about multiple regression, you know how that works, right? So you've got a set of variables, and you can turn it into, you can work out what a dependent variable will look like depending on what the inputs are, what the independent variables are. So, for instance, you can also use that to work out whether people are going to respond well or poorly to your visualization based on the variables that you're giving them. So you can tell, you can have a guess, you can model whether or not people will respond better or worse to a change by running it through the regression, potentially. I haven't seen a good example of that working, but I'm told it works. So if you find a good example of that, then show me. I can see how the principle might work, yeah? Do you see how that could work? Okay, good. Right, then user studies. So this one is quite simple. You basically give people things and see how they cope with them. So this is the sort of thing that you're most likely to do. Show your work to somebody else. So the most important thing about that, I mean, there are lots of important things, but one important thing to remember about this is that if you show this to your mates and say, hey, look at this map that I made, or look at this visualization that I created, what do you think? Then they are not likely to say that it's rubbish, unless they're that kind of friend. They might want to be nice, or they might be hypercritical because they think that's the nature of the relationship. Okay, they might just, that's more likely. Say, okay, right. So they might subject it to some banter rather than having something useful to say. Right. You might want to think about how many people you can ask to do that. So you're going to ask every member of your family, and will you find out anything different? Or, you know, who are you going to ask? How many people can you ask? So you take all that into account, and let's say you want to test out some kind of visualization. You've got 6 symbols, and each of those symbols has got 4 different levels. So that straight away means that you've got over 2,000 different testable objects. And let's say you want to take 10 measurements of each, and each measurement is going to take 30 seconds. So now we're up to 160 hours worth of evaluation time. And if you want to do that with 15 people working as fast as you can reasonably before you have to start paying them a pension, then you are going to take about a year to perform your visualization. So make sure that you're testing a small amount of things with a large amount of people, or a large amount of things with a very small amount of people, and don't ask them to spend very long on, you know, make sure that you've set up the test so that it takes you less than a year. And you also want to have control. You want to set up controls. So are you comparing it with something else? Are you comparing it with nothing, as in what's better, nothing or this? Or you might want to be testing it with the previous best version to see whether people perform better with yours or the best old method. Okay. Here's an example. If you follow this link, evaluating the usability of visualization methods in an exploratory geovisualization environment. So I highly recommend you have a look at this one. It will give you that's KUA, K-O-U-A. And of course, you can also download the slides and follow the link, won't you? Okay. Well, you know, he's busy doing his evaluation with 15 subjects at 160 hours. So. Yeah. So here is plenty of, you know, you'll be able to work it out for yourself if you read the paper, but. Tasks given might be locate, so find where this thing is, or identify, so tell me what's at this location, what's the difference between, you know, distinguish between things, categorize things, does this thing belong in that category or that category, Is it part of a cluster or not? Which one comes first? What's the highest? What's the lowest? Which one's higher than this one? Which of these two or more are higher? Which one goes with this one? Which one doesn't go with this one, etc. So, identify possible relationships between population density in the coastal region and GDP per capita, and then you give them a map, and then you get them to work out how, you work out how long it takes for them to work out that relationship and how well they do it. Yeah? So you show them your map and you say, which 5 of these countries has the highest GDP? By looking at a map like this. Well, this map actually shows you the percentage population within 100 kilometres of coast or river. But, you give them the map and you get them to work out the thing that you're trying to get them to work out. And see how long it takes and how poorly they do it. Or, what's missing? Where's the missing data in this map? What's wrong? What the errors are. The map is the visual representation used in the test. Sorry, yeah? I forget, it's been a while since I looked at this. But these are all representations of the data itself, yes. Sorry? A is the map, yeah. B is a parallel coordinate plot. Have you come across parallel coordinate plots before? They're quite nifty. Instead of plotting like the classic map with 2 axes, you put the axes next to each other and then you can have lots and lots of axes and you can kind of see where things go together. But the order of the axes is quite important, and sometimes you can end up with a big horrible mess. But here you can see that most things, for instance, I don't know what these variables are, but lots of things share these, low numbers of these and high numbers of these, but there's a wide distribution of these values, but not of these values. Do you see what's going on there? No? Okay, so normally you would have X, Y, like that, right? Get the pen out. Okay, so normally you have your data in a plot like this, right? But you can shift one of these axes to here, right? It doesn't have to be there, it could be here instead, i.e. here. So then you can draw a line showing that the thing that's got that value there has got this value, that's one case, and then there's another thing that's got the same value of that, but it's got that value of that, right? And then you can do that, and it turns out that they're all over the place, or whatever, but there's a much wider range of values on this axis than on this axis, okay? So then you can add a third dimension, right? Okay? And then you can say, but all of these have got, it doesn't matter what the value of that is, they've all got very low one of these, and they've all got very low one of these, whatever that is, and so on, right? So you have your multiple dimensions all plotted. You end up with it looking like that. 60. Oh, in 6 dimensions. Yeah, it could work. Well, how many are up there? A dozen? It kind of depends on the data as well. So you plug in the data and see if it comes out. SPSS will do this for you. Using the, I forget what it's called, but there's a kind of template thing set up for, what do they call it? The template board or the work board or something like that? No? Okay, well, have a look on SPSS. Also, those EDA things that we looked at a while ago. Do you remember the exploratory data analysis thing? Another year, another world. In another life, we talked about exploratory data analysis, and I showed you GeoDar and GeoVis. Right, okay, well, thanks for remembering it. GeoDar is a bit unstable, but quite nifty if it works. Yeah, so as well as cartograms, which I quite like in certain circumstances, you can also do that. And you can also do these. All of these are available in, maybe not yeah, I think pretty much I will do most of these visualizations, but it's certainly worth looking at. Because it does it quickly, and then it crashes, but hopefully you've got a screenshot before it crashes. Yeah. Okay, so for Friday, also another life. This week's practical: design and evaluation for your geovisualization challenge. What are you going to do? Because you are going to need to evaluate it. In 2000. You've got to write 1,500 words evaluating your visualization. So, or whatever. What do you mean, or whatever? You've got to write about whether it's any good, right? So, why not design an evaluation, okay? And even if it's really worth doing an evaluation. So hopefully now you've got some ideas about how you're going to do it. Well, you could ask 100 people to use your... This week's practical, design the evaluation, okay? No, but you might want to design an evaluation and at least discuss how it could be evaluated and what you might expect to learn from the evaluation. Okay? So all you need to do for the practical is design an evaluation. Okay? Well, it's up to you whether you want to do the work or not. But this will be useful. Okay? If nothing else, at least you'll have an idea about who you could ask and what the limitations of what you can do would be. So if you end up asking 5 of your mates and your family whether they can use your GeoVis challenge, then you will be aware that they might have certain biases, for instance, and you can take that into account. You could show it to a load of you could show it to somebody, and under a certain degree of controlled conditions, you could say you could find out at what point they can work out what the colour of a feature is, a small feature, or whether they can tell the difference between the doors and the windows, these kind of things, right? No, I know, but so. Yeah, but the earlier you do, but if you design your evaluation while you're designing the challenge, then while you're designing your project. So you haven't started. Well, if you develop them at the same time, then they can work together. You can think to yourself, is this an evaluable? Is it possible to evaluate the thing that I'm doing, and how? Right? Because if you leave it till afterwards, you'll be like, well, I've done this thing, but it's impossible to test whether it works or not. So make something that's testable. How are you going to do that? By thinking about whether it's testable. You've got to talk about what... Yeah, so what would the purpose be? What might the purpose of your visualization be? To find out if what, sorry? What 3D exists in Bridge Street? Well, to find out what the buildings look like. When you've mangled them in SketchUp. Is that what you mean? Okay. Well, if your tools aren't working, if you haven't got very far with it, then and you're not sure what the point is, then think about you could do something else. What's the point of it? Decide on the purpose. It might, yeah, it could be a theoretical purpose, but have one in mind, okay? Have one in mind. Could you make up a building? I guess technically, look, you'd have to talk to Dave about it, but technically you could do a fictional building if you've got a reasonable description of the building that you could borrow and, you know. Sorry, what's it? If it gets to the stage, we'll talk about it. Talk to Dave about the technical problems. Okay. Okay. Right. Your what? Sorry.
Your building's
okay.
Got loads of windows.
Anything else I can help with? Look, if it's seriously.